So last class we saw how the X-ray works. One of the key primary thing about X-ray is that X-ray is a 2D scanning for a human body. 2D scanning means it scans one planar view of a certain object or a patient in a photographic plate. So you have length and width, you have a flat image from which you have to gather data. Sometimes for required cases where we careful. So sometimes for more precise the diagnosis process, we have to have three-dimensional scanning, which scientists developed, and that how can we do a three-dimensional scanning of a patient or human body structure is basically what CT scanning is all about. CT scanning, the elaborate form is computed tomography. The idea of CT scanning is actually pretty simple. I'll tell you the basic idea first, and then I'll try to make sense with you. In the CT scanning, an object would be scanned 4 times, which will give us information about the object for 3 spatial direction: x-axis, y-axis, z-axis. Now, you might wonder, we are scanning 4 times, we're going to get 3-dimensional information. That doesn't sound right. Where does this extra 1 come from? The first scan that we do of an object, I mean, I'll show this to you in terms of content or in terms of voxel as well. Whenever we do the first scan of the body, we get the primary number or primary set of values to work with. This is sort of like scan 0, if I may, or if you want to think. This is the this creates the value of the location for one linear aspect, which we get a combined value for one row or one column, and then we extrapolate those information to a possible amount of further boxes. এই কথাগুলো কিছু বোঝা যাচ্ছে না আমি জানি, but I'll make it understandable to you. Just bear with me. So with the first scan, we try to remember, understand this. With the first scan, let's say 0 number scan, the very primary scan, we build up the ground information with which we're going to work for the CT scan. Then comes the x-axis scanning, y-axis scanning, z-axis scanning. With these 3 different axis scanning, we get the additional data we need to input to that ground data, which ultimately adds up to the process of detection. That we're going to have to do 4 different scanning, which is shown over here. Let's say for the CT scanning to work, it's a very precise work. I mean, it's a very precise work. And for a regular X-ray, earlier when digital X-ray was not available, this was the process that we have the X-ray tube. So we have the collimator to making the parallels, and then we have some aluminum sheet over here to absorb the weak X-ray beams, which will only add to the radiation dose of the patient, which we don't want to go through. So there is an aluminum sheet over here, and then they have the collimator. The parallel beams of X-rays are sent to the patient's body. Beyond that point, we also have one set of collimator over here. There should be another collimator over here, which is not shown in the figure, but there is usually another collimator right over here. And then, other than having an X-ray plate, we're going to have an X-ray detector. So this X-ray detector is going to be something like the CMOS sensor that I told you the other day. That other than having a physical X-ray plate, which is going to work pretty much like a cellular camera, we're going to have a digital X-ray, digital sensor, pretty much like what happens in a digital camera or a video camera or like a cell phone. So each of the pixels are going to pick up a certain value of the X-ray photons, and it will be able to remember that information. And this is the information that we'll be working with. So these X-ray detectors are capable of getting a person's inside information in terms of how much radiation could pass through a certain location. Now, what do I mean by this? That whenever I say through a certain location, what does this essentially entail to? Important bit that you really need to understand that for the case of a 2-dimensional image, we use the term pixel. Now, the term pixel is essentially applicable for a 2-dimensional case. 2-dimensional case means that whenever you guys know what a pixel is, right? Everyone? Do any of you do not know what a pixel is? No one is responding apparently. So I have no idea what to make out of that. Okay, Abias wrote is a square. I'll tell you anyway. Pixel for a two-dimensional picture is the smallest section of square which can hold one color. So let's say this image, this video feed that you're seeing, this is a 50 hertz screen sharing, which means you are having 50 images of this thing every second, making it a video. And each of this image is full HD. Full HD means 1920 by 1080p, which means each of the image that you have, and if I take a screenshot, if I press print screen, and eventually if I go for example, if I do the print screen right now, I did that, and now I'm going to paste this information into MS Paint, and I now have it. So you can see that over here we have a pretty large, pretty beautiful square for the red and green, your screen sharing, blah blah blah. Everything is showing up. Now if I start to zoom in, you'll see that this is starting to crack up. It's no longer a smooth cross. This line is a smooth thing. Have a look. This thing. I mean, this is highly zoomed. This is 700% zoomed. You can see that this whole select has become not so beautiful. I mean, in layman's term, what we say is that the picture has broken, or বাংলায় বললে ছবিটা ফেটে গেছে। ফেটে যাওয়ার বেসিক্যালি এটা হচ্ছে যে এই ছবিটা এই যে এখানে যে বক্সগুলো আছে, for example, if you try to have a look over here for the structure of this letter T, you can see that there is one vertical line of one shade of color. Then there is another lighter shade, and there are these, you can see rectangular shapes over here. Each of these rectangular shape happens to be 1 pixel for this whole picture. Each of this rectangular shape, and one of these rectangular shape is gonna hold one specific color. Acha, beautiful. One of the pixel, one of this rectangular box is gonna hold one specific color, and whenever we're gonna stack up multiple of this image of these things side by side, we're gonna end up with the whole image. So this makes, because this is very much like a graph paper. So if whenever you see at this picture for this full HD, it looks pretty smooth and beautiful and curved and whatnot. But whenever you start to zoom in, things starts to break down. For example, have a look. This thing is not apparently looking to have so beautiful of a structure because we have a limit for pixel. The idea for this image is that this is a, if I go over here, you can actually see the size of this thing. Where is it? Resize exactly. So we go for pixel. Have a look. This image has 1920 horizontal pixels by 1080 vertical pixels. That's the picture resolution, or that's what I call the full HD resolution. Not 4K. 4K is a different thing. So এটা হচ্ছে পিক্সেলের আইডিয়া, যে একটা সিঙ্গেল বক্সের একটা স্পেসিফিক ভ্যালু আছে, এবং অনেকগুলো এরকম বক্স যখন সাইড বাই সাইড বসাবো তখন পুরোটা মিলে আমাদেরকে একটা কম্বাইন একটা ইমেজের একটা ইনফরমেশন দিবে। নাও ফর দ্য কেস, this equivalent thing of pixel for the 3-dimensional case is what we call voxel. Voxel is basically the, I'm going to close it off, I don't need that anymore. Voxel is the pixel equivalent for a 3-dimensional case. Now, what do I mean by pixel equivalent for a 3-dimensional case? It means that for a 2-dimensional case, you're only going to have a square that you have to deal with that should have a specific color. For a 3-dimensional case, you have x-axis, y-axis, and then think about the z-axis. So if you have a large cube that is broken down into smaller cube structures, each of those small cubes can work as a voxel. And how small that cube is going to be important for how good of a scan image, 3-dimensional scan image, can you make. For example, if you think about, let's say I'm trying to have a CT scanning of myself. Now, if the computer which is handling this information, X information, can only work with, let's say, 4 big chunks of voxel for my belly, let's say on the, I mean, think about it, let's say here is my belly, and then here are 4 voxels, like with a cross at the middle. Then we're gonna only have a very weird CT scan, because that picture is not gonna be worthy to diagnose anything. But we can have that. That's a very large voxel size, because the huge amount of mass has been broken into too few number of pieces. If we reduce the number of pixel size, I mean voxel size, it means the smaller the size of the voxel, or the bigger number of voxel we're gonna scan, the more precisely we should know that in which locations do we have bones, in which locations do we have tumors, in which locations we have blood vessels, where we have nerve endings, blah, 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 blah. So making the voxel size small is beneficial for us. But when the moment we start to make the voxel size smaller, the calculation or the math or the data that we're going to produce is going to become big, which is obvious that we have a more detailed image, which means we have to handle a much bigger amount of data and be able to process that with appropriate efficiency. So that's the idea of overvoxel. Now, to make sense how the calculation of the CT scanning works, we are going to primarily start with this kind of a voxel size. Now, what I want you to understand that this is a certain voxel values which currently is given to us so that we can understand the math behind it. In a realistic case, we would not know this thing. We would not know that we have 4127 kind of voxel values for these 4 boxes. We would know that in terms of physical volume, there are 4 voxels over here. We would know that. But we would not know that these are the values. There will be processes, sequential processes, which will lead us to assign these values. Now, how would that calculation lead us to assign these values is something we're going to learn. And to learn that, we, for the sake of understanding, we assign these numbers in the first place. এটা কেন করছি সেটা আমি লেকচার মানে শেষের দিকে গেলে তোমরা খুব ক্লিয়ারলি বুঝো, বাট ফর দ্য টাইমিং এই জিনিসটা বুঝো যে এটা শুরুতে আমাদের কাছে অ্যাভেলেবল থাকবে না. We would just know, let's say in this case, just to make the calculation simpler, we are working with 4 voxels over here. I mean, you can stack up with 3/4, you can stack up with, let's say, 2000 by 1000. You're going to have a similar kind of calculation. So you can have a much bigger number of voxel with a smaller voxel size, depending upon how precisely you want to scan that patient. And we're going to get to these numbers by calculation, where these numbers will not be readily available as it's shown over here. Now, voxel equals volumetric pixel. Yeah, exactly. So 3-dimensional pixel. Thank you, obvious. So how does it happen? First, we are sending a horizontal beam to this amount of human tissue. So let's say now, this is the part that I want you to understand, that the machine or the CT scanning machine or the X-ray photographic sensor that has a capability for how many voxels can it sense in a given space. So depending upon its capability for the sensor of the X-ray beam or X-ray detector, depending upon its capability, we would know that how many voxels do you have within a human body. For example, this view that you are seeing over here might as well be as an insanely magnified view for an actual scan. What do I mean by this? Let me show you a bit of information, so it might actually be understandable. Let's say this is a human patient. These are not sheep, these are legs, hands, and hairs. Okay. So let's say we are about to do a CT scanning of this patient for this much size of his body. So we want to make a 3-dimensional scan of this much size of the body. So you have to think that this is a 3-dimensional thing, although I'm showing you this whole thing on a 2-dimensional figure. So if I try to get a 3-dimensional axis system over here, we're going to scan it from 3 different axes. So I cannot actually physically very efficiently draw the 3-axis system over here, but I can actually try. Thank you. Let's say with a different color, maybe it should be better. So let's say this is our y-axis, this is our x-axis, and let's say this is our z-axis. So you can name any of them anyhow, but they are all perpendicular to each other. We have to align this patient in such a way that we are going to scan this person through these three axes primarily, but these are going to be our scan number 1, scan number 2, scan number 3, but we will also require scan number 0, which should happen in any random direction. If you wonder what does it mean by random direction, that random direction would be the first set of scan that we're going to do, which is not going to be along any of these lines. So I mean, if I try to make better sense with you, have a look. This is the first scan that we do, or this is the primary scan or scan 0 number scan that we do, which sends a beam of X-ray beam through these 4 voxels through the patient, and on the receiving side we're gonna get a total voxel values of 5 and 9. Now, if you wonder what does this voxel value mean, I mean, what is this thing? Is this a currency, or what is this thing? The voxel value is basically a measure of how much the tissues absorbed or how much the tissues allowed to pass. I actually forgot what is it. Well, wait, I'll look up this information. I mean, actually ভুলে গেছি. খুঁজে পাইতেছি না. What your PDF or your information only says that the aim of a CT scanning is to make an image of a section or slice to the body for measurements about its axis, as illustrated in figure 2.7. The section or slice through the body is divided up into series of small units called voxels. The image of each voxel would have a particular intensity known as vox pixel. So they have used this word particular intensity. I'm not sure, I actually forgot that these intensity numbers that is shown over here do they represent the transmitted intensity? That means how much that was allowed to penetrate through the patient and eventually come out on the other side, or does it mean the absorption intensity? Each time ভুলে গেছি. So আমি এটা পরে খোঁজ করে তোমাদেরকে বলবো. For the time being, not to waste time, this is something that you really don't need to know, but it actually helps if you have a specific information. It really helps. But for that, I mean, let's assume these numbers that we have over here represents the absorbed amount of X-ray, which means you have a much highest amount of absorption over at this tissue for this in this voxel, least over here, and the other two tissues have 2 and 4. So you can pretty much think, I mean, if you think in terms of human tissue, I mean, we are not altogether made with solid object. Inside our body, we have gaseous spaces where we have extra space. For example, half of the lungs are full of gas. Then the coelom is full of gas, and then the stomach upper half, because we don't always stomach is not always filled, so some part of the stomach is always also filled up with gas. So if you try to think about it, it might as well be a bit easier. Let's say this is a piece of bone, maybe this is a bone tissue, have a very high value of absorption, 7. Then this one might as well be, let's say, maybe a bit of a fat, which has a very smaller density. This might as well be very, this might be a piece of muscle. This might as well be empty space. So what I want you to visualize, just for the sake of easy understanding, that we have 4 different type of tissues over here, which have 4 different type of what is this called, intensity values, or voxel intensity values. So we want to find out these numbers, that exactly what are these numbers are, but we would not know these numbers to begin with. So what we know to begin with, first thing, we're going to send a beam of X-ray through these voxels from the side, and we know specifically that the amount of space or the size of flesh that we are handling right now has exactly 2 by 2 voxels in it, and we are sending the beam from the side. So this will divide the entire patient's body into sections, which is gonna lead up to these 2 numbers, because whenever I'll send X-ray beams to this from this direction, to understand, this X-ray beam would be simultaneously absorbed by 4, this tissue part, and it will be also absorbed by this tissue part as well. Together, they will make a total absorption of 5 value. And this horizontal beam, I mean, this is the same beam that is being sent with the same initial amount of intensity. And this line, along this line, the absorption was of 5 units. Along this line, the absorption was of 9 units. That's the difference. So we now have this set of information. We do not know yet how much is this, but just because we wanted to calculate, we did have these numbers. But to be honest, once we do our first scan or 0 number scan, the first set of detector readings, we're gonna get these 2 numbers. So what I need you to understand, we actually have, along this line, we have 4 voxels, but we're only getting 2 numbers over here. So we have to somehow start working with this number, and just to get the working started, we'll simply duplicate this thing for a second row. So this information or this radiation value that we have, we're simply gonna duplicate this. So whenever we'll duplicate this thing, we're gonna consider for the time being that these 5 voxel values have a value set of 5599. So we simply doubled up the total amount of radiation. So this is the part that I want you to understand. If you try to think about it, the total amount of absorption value for these 4 voxels together was 5 plus 9, 14. This is what we call background intensity. Background intensity, is that the word? Background intensity, yes, take a sec. The total amount of absorption of the X-ray beams is what we call the background intensity. In this case, after doing the first set of detector readings, we get that the total amount of absorption value is from this 4 voxel is 5 plus 9, 14. And we simply doubled that column. So we have made a 14 amount of pixel value more into this column. This would later have to be dealt with, that this amount of addition that we are bringing in the first place, we'll have to deal with it later. And how we'll deal it, I'll show it to you, but why is it dealt in that manner, or why that process actually is valid, is not discussed in your syllabus. So if you ask me a lot of whys for the later part of the lecture, I might not be able to answer that. Just a quick disclaimer to at this point. But if you are curious to find this out, we can search up the internet and get to the bottom of this thing if you really want it. But I'm going to show you the part that you need for your syllabus volume. So we have 5599 over here. We just doubled up this column value, radiation value, and we get these voxel boxes. Then we're going to send angled X-ray. So in this case, the patient is basically undergoing a second set of X-ray. So to make the CT scan possible, you are going to scan the patient 4 times within the same device, within the same machine. This is why CT scan machines usually look like those very round stuffs where you make the patient lie down in a certain, I mean, if I want to show you the physical view of a CT scanning machine, you see, this is how a CT scan machine looks like, which is quite similar for how does an MRI machine looks like. They are pretty similar looking, but there is difference in their working. There is very precise difference in their working. Have a look. This is how the MRI machine looks like. Same stuff. You have a bed, patient goes in the bed, and then this bed slides into the MRI machine along with the whole patient, and the machine does its magic, and you have data. And also for the CT scan machine, similar. You can see that there's a hole, patient goes in, machine does its magic, and you get the data. So basically, they pretty much look similar, but they are not essentially the same. They are not essentially the same. That's the important bit that you really need to understand. And what is also pretty important is that within this device, within this donut-shaped thing, we have the X-ray sender and X-ray receiver, something that is shown over in this place. So the patient is kept stationary because we don't want to cause discomfort in the patient. So other than having the X-ray setup fixed and rotating the patient, we're going to keep the patient stationary. The patient is going to lie down on the table, and we're going to rotate the setup for the sake of comfort and easily accessible, or I mean, for the patient's comfort level or whatever. So that's the idea. So we're gonna rotate the whole the direction of the X-ray sending, and we're gonna send a corner beam to this same voxel, and we're gonna get 3 different readings. Have a look. The beam that's gonna pass through this along this diagonal, that's gonna have a direction value of 1. The one that passes through the middle along this line is gonna have a total absorption value of 4 plus 7, 11. And this one is going to have 2. Now, the machine is going to, from this 4 voxel, which means 2 by 2 voxel, now we're having 3 reading. You have to understand why 3 reading, because we have 3 different alignments of absorption. One alignment is for 1, the second alignment is for 4, 7 together, diagonal alignment, and the third one is for only for this last voxel, 2. So we have 1, 11, 2. We're going to add these voxel values. We're going to add this we're going to add these voxel intensity. Intensity to na ki jeno bollam word ta intensity. We're going to add this diagonal voxel intensity with the original made up box of 5599, and we're going to add these things over here diagonally. So what does this diagonal addition look like? What does this diagonal addition look like? Have a look. We're going to add 1 with 5 is becoming 6. We're adding 11 with both of these numbers. Important. We're going to add this 11 with both of these numbers. So 11 plus 5 gives you 16. 11 plus 9 gives you 20. And 2 will be added with the lower diagonal box. So 2 plus 9 gives you 11. So that's the diagonal addition of this reading to the original box that we have got. এই পর্যন্ত addition এই পর্যন্ত বুঝা গেছে কিনা? It's important that you understand up to this, otherwise the later part would not make sense. If any of you have any question, this is a good time to respond. Anyone? Any questions so far? What's the purpose of the addition? Acha, addition এর purpose টা একটু পরে clear হবে. Purpose টা আমি বলবো, which will be clear at the end of the addition process. We have 2 more pages to go by. But additionটা কিভাবে হয়েছে এটা বুঝছো কিনা?
জি স্যার।
Acha, beautiful. So what we're gonna do, we're gonna do another set of scan right now. So I'm moving on since none of you actually asking a question. So I hope it made sense more or less. So we are now sending we're now sending another beam in the vertical orientation. So this is gonna give us 6, 8. 4 plus 2, 6, 7, 1 plus 7, 8. So we're gonna add this thing with these voxel values, which is gonna give us 6 plus 16, 22, 6 plus 11, 17, 8 plus 6, 14, and then 8 plus 20, 28. So you're gonna add up the scan value with all the voxels on its path. That's the important bit. You're not gonna add it only with only one. Whenever we did the diagonal scanning, we got 1, 11, 12. 11 was in the path of 2 voxels. We added this 11 with both the voxels. Now in this case we have got 6 and 8, which is so 6 was added to both of the values. So you have to understand that this thing is this thing. So we are consecutively adding up the scan values onto the single voxel calculation. This is something that is kept within the computer's memory, and the X-ray machine computer is gonna handle this data and do this addition on its own with some appropriate algorithm, of course. So, but how does that algorithm work? That's basically what we're trying to show you over here. And we're only choosing 4 voxels over here so that the calculation is understandable to you. It's not too much complicated, because what happens in 2 voxels basically happens over in, let's say, 1000 by 1000 voxels. The process is similar, but the more voxels you have to handle with, the more complicated it becomes, which I'm going to show you with some example after a while. So here we have, so we're adding 6 plus 8. So we get this new voxel values. Then we're gonna do our last scan. So this, which is happening from this corner, and we're getting 4, 3, 7, 4, 2 plus 1, 3, and then 7 is still 7. Then we're gonna add this 4, 3, 7 with this pre-obtained voxel value in this direction. So 4 plus 22, 26, 3 plus 14, 17, 3 plus 17, 20, and 7 plus 20, 35. This is the end result that we want to get. So this is the final voxel box calculation intensity values. Once we have done 4 of our scans and we get this value, now comes the final leg of the calculation. Have a look. The final pattern of the pixels is shown in figure 2.13. So we have this value. In order to obtain the original pattern of pixels, 2 operations must be performed. First of all, the background intensity must be removed. The background intensity is the total of each set of detected readings. In this case, 14 is detected from each pixel. So 14 is detected from each pixel. So 14 was the original background intensity, which is over here. So this is 5 and 9. So we actually made a secondary column, which means we actually increased the value of each of the pixel by 14. So because we just double this thing. So now we're gonna subtract 14 from each of the boxes. Now the question is, why from each of the boxes? I do not know the answer, but the process that follows is that we have to subtract the background intensity, which is the total intensity value from the very first scan or 0 number scan. We're gonna subtract that number from each of these boxes. And if you wonder that is it possible to have negative values, no, you're never gonna have negative values, because that's not how the device is designed. You're always gonna have over here some value which is definitely bigger than the background intensity. You will. So we're going to deduct 14, this is the first thing, and then after deduction of the background, the result must be divided by 3 to allow for the duplication of the views of the section. So after deduction, we're going to get this number. So we have deducted 14 from all of the boxes, each of the boxes. So we get this number. And beautifully enough, now all these boxes have become multiples of 3, and this will always happen. At least for your level, you're not going to handle with decimals. For your calculation values that you have to perform for your test, you'll always be working with integers. So this number will always be fully divisible by 3. Now we're going to divide these values by 3 because we did the scan for 3 axes, and then we get 4127. So this is our end result. This is something that we are going to get out of this whole process. And now we know that these 4 individual tissue pieces that we are now trying to scan through the CT scanning has this value of pixel intensity. Initially, we did not know this. You have to understand this. And this thing is the calculator. We came to know about these 4 individual values after doing all of this calculation. We did not know these values to begin with. What did we know? When we were starting to scan the patient or scan these 4 voxel of tissues, we first knew only 5 and 9. We did not know the individual values. The reason we are provided with the individual values so that we can make sense that how did we get to 5 and 9. So machine did not know this 5 could very well be any value of pairing over here. This 9 could as well be any value of pairing over here. The machine does not know 4127 to begin with. The reason we are provided with 4127 so that we can make sense of the calculation process. That's it. So originally আমাদের voxel value গুলো জানা থাকবে না, voxel value গুলো বের করার জন্যই আমরা সিটি স্ক্যানিংটা করতেছি। How does this help us to do that diagnosis? The idea is very simple. We know how a typical or healthy person is supposed to have those values aligned in a certain person or certain location of their body. I mean, the way the computer works is that this is basically we are knowing the pixel values for 4 different voxels for one orientation, and then we can have this thing for multiple. I mean, it could as well be a 3 by 3, it could be 4 by 4, it could as well be, let's say, 200 by 170 or something, because you might as well be scanning a rectangular portion of a patient's body, not necessarily a square portion. So depending upon how much size of the tissue that we are trying to scan and the sensitivity of the sensor that we are going to using in the X-ray detector, we can have a lot of different X-ray values, but the process will remain the same. We're going to do our first scan, we're going to get a bunch of numbers, we're going to duplicate that thing to the number of voxels that we know physically exist within that amount of flesh, physical tissue, and then we're going to do 3 more scans, and we're going to do those diagonal addition to all of those, and eventually we're going to have a large amount of value for the voxel box, and we have to এক minute. Sorry, I have to scream to my cat. কি বলছিলাম? All right. হ্যাঁ, সেটা হচ্ছে যে and eventually the calculation will become much too big and difficult. Here we are working with only 4 voxels. That's why it is at least to some extent it is understandable that how this works. The moment you're going for a bigger number of voxel values, you're going to end up with a much bigger amount of numbers. For example, if you just think that if we simply want to take, let's say, a 3 by 3 box, try to understand the amount of complexity that we're going to have to handle. If we just go for a 3 by 3 box, how does the calculation for 3 by 3 box work is not essentially needed for a syllabus, but I have to proof check one of these things, which that's why I'm not showing you the one sample of calculation right now in today's class. আমি একটা জিনিস চেক করতে ভুলে গেছিলাম, সো আমি এটা চেক করে নেক্সট ক্লাসে দেখাবো। But what I want you to understand that if you're going for a 3 by 3 voxel more rather than a 2 by 2 voxel, after doing the horizontal scan, you're going to get 3 set of values. So you're going to have 3 values over here, and then you have to simply copy this thing into 3 by 3 columns. So you have to get these same numbers over here and get this whole thing. This will be your functional chart to begin with. Then as you scan from, let's say, in this direction, you're going to have how many numbers? This thing that you're going to get, this diagonal list will have how many numbers? Have a look. You're going to have 5 numbers. Why? One set of ray will pass through this direction, one set of ray will pass through this diagonal direction, one set of ray will pass through this diagonal direction, and then this one, and then this one. So you're going to have 5 different numbers over here, and you'll have to add these 5 different numbers with 5 different alignments of these boxes. So that's big. If you have more than 3, if you want to work, let's say 4 by 4, then you're going to have even bigger numbers. You have 5 by 5, you have bigger numbers. So the calculation is extremely large to begin with for the practical purposes. For all reasons and purposes, the numbers that we're going to handle for a practical CT scanning process is actually very large. That's why it is never done by humanly, it is done with the computer, and ultimately this leads up to the value of the voxel values or intensity of the voxels. Yes, Abias, go ahead. I'll take questions. Hold on, I'll try to answer obvious questions, but I want everyone to read these two paragraphs at the bottom of this thing. If you have any question from these two paragraphs, you can ask me. Yes, Avias, go ahead. Hello? Oh, you're writing up. Sorry. Yeah, sorry. It says, was this done to translate the density of the maximum body? Yeah. Essentially, yeah, exactly. So we are, I mean, I would not say it's basically the physical density, but it's somewhat of a absorption coefficient, or it's somewhat of a measure of how much X-ray beam was absorbed within that segment or within that voxel of the human of the body tissue. So if you want to think in terms of density, it actually is easier for us to understand in terms of density, but it's not always density, because a certain tissue type can also be physically less dense, but more absorbent for the X-ray beams. Cancer cells tend to behave that way. That they don't have physically more density, but they tend to have more absorbing capability compared to the other body cells. So yeah. The answer to your question is yes. Which leads me to the other part that I actually derailed from while I was talking through, is that we know how different location of the human patient's of a human body should have values. I mean, how does the lining of a stomach looks like? How does that continuous data stream should appear for to be stomach? How does the whole intestine looks like, or how does the liver looks like, or different parts of the liver should looks like? So whenever we do the CT scanning, if there is a certain tumor growth or certain additional stuff, which is or some external body, let's say a person got shot by some their sharpness in their body, we do the CT scanning and we'll be very precisely can look at exactly in which three-dimensional coordinate that a specific object is, which is not supposed to be there, which is the anomaly for that person compared to a healthy person, because we can compare those values for with a regular person's value that we know from earlier scans, and then we can know that, well, this thing is not supposed to be there because this apparently is the anomaly. So we would know that it might, and depending upon how much absorption do we have, we can also consider, is this a certain crystal? For example, you can have crystal grown up in kidney. Kidney stones are actually physical stones. I mean, they are what can I say? They are the accumulation of some sort of carbonates and sulfates together, and which gives rise to crystals. So kidney stones are actual kidney stones. Gallbladder stones are actual stones, but then again, the physical tumor is basically basic human tissue. So you have different range of absorption behavior for different type of anomalies that you can have, and from those anomalies, doctors can actually predict what is there and precisely at which location, and we can go for to take that diagnosis. Abhi, did I get your question answered? Oh, it's all right. So it's all right. Questions are welcome in the chat window as well, as long as we all make sense. Everyone else, do you have any further question? This is basically the end point of the CT scanning process. We're gonna get into the physiology. Bolo.
আপনি ওই যে 45 ডিগ্রি রোটেট করার পরের এক্সপ্লেনেশনটা একটু বলেন তো।
কোনটা?
ওই যে স্যার 45 ডিগ্রি যে রোটেট করলেন, তারপরে যে আবার মানে we had to add up things. Yeah, ওই এই যে নিচে এই যে নিচে, হ্যাঁ, এই পার্টটা
এটা হচ্ছে যে first we're gonna do one set of scan, and that's gonna give us a ground value to work with, and then we're gonna do 3 more scans from 3 different orientation, and we're gonna get some diagonal values or horizontal values, and we're gonna have to add those numbers in that same direction with the original table that we got.
স্যার ওরা কি ভ্যালুগুলো দিয়ে দিবে স্যার?
আচ্ছা, অ্যাকচুয়াল ওয়ার্কশিটে এই প্রবলেমগুলো কিভাবে সলভ? ইটস এ ভেরি গুড কোশ্চেন। অ্যাকচুয়াল ওয়ার্কিং এ তোমাদের কিভাবে সলভ করতে হবে? ইটস এ ভেরি গুড কোশ্চেন। I'm going to show you one sample or 1 or 2 sample right now, so that it's easier for you to deal with whenever you come across this question. Because why not? দেখাচ্ছি আমি, just a second, একটু ওয়েট করো। আচ্ছা, এটা মনে করা হচ্ছে যে কোশ্চেন নাম্বার 3, এটা হচ্ছে আমাদের একটা সিম্পল সিটি স্ক্যান রিভিউ। A simple model of one session of CT scan is shown in figure 10.1. The model consists of 4 voxels with pixel numbers A, B, C, D in clockwise format. Okay. In this model, the voxels are viewed in turn along 4 different directions, D1, D2, and D3, as shown in figure 10.2. The pixel readings in each of the 4 directions are noted. The total pixel reading for any one direction is 19. এই যে total pixel reading for any one direction is 19, this is the measure for the background intensity. So এই ভ্যালুটা তোমাদেরকে অলরেডি দিয়ে দিছে। And then they are giving us the pixel readings for all the directions are summed to give the pattern of the readings shown in figure 10. So which means in this question, in this particular question, they have given us the value of the background intensity, which for this table was 14. So if you scan from one direction, you get 5 plus 9, 14. If you scan from this direction, you get 11 plus 1 plus 2, 14. If you scan from the top direction, you get 6 plus 8, 14. So in the total absorption value or total pixel value for any one direction is what we are calling the background intensity. And that is given, and they have also given us this final output, the total summed value for all the 4 directions. So we are provided with this number, and we also provided with the 14 number for this example, but for the question, this number was 19. So we're given this whole value, and then we are told that the background intensity is 19. So the question says, set the background reading of this model 19. You just write 19 over here, get 1 mark. Beautiful. Determine each of the pixel readings. So তোমার কি করা লাগবে সবগুলো you just what do you have to do? You have to subtract 19 from all of these boxes, each of these boxes, and divide the remaining values, the subtraction results, by 3 to get those pixel values. So that's the calculation that you're expected to do over here, and eventually you should get these numbers over here. So you can do the calculation in your calculator. You can do the calculation at some blank space of the question paper. You can do the calculation right over here with pencil. The examiner doesn't mind as long as you come up with correct numbers. Because if you have a look at the mark scheme, I'm going to look at whether evidence of working is needed for this thing or not. I'm pretty sure evidence of working is not needed, but I'm still going to look for this. Question number 3. So it says that ABCD values are given. Allow 1 mark if only subtracts background reading. So if someone does not divide by 3, then they're going to get only 1 mark for the whole question. You have to do the subtraction, then you also have to divide them by 3 to get this number. So evidence of calculation is not apparently needed. So it says, well-prepared candidates with the required knowledge of how pixel readings are developed for the CT scanning often receive full credit for the answers. However, candidates possessing only a superficial knowledge of scored comparatively few marks. Such candidates would benefit from practicing answering this type of question when they are initially developing the understanding of CT scanning. Well, so you do not have to have evidence of working, so which means you can just write up these numbers and it's good. বুঝা গেছে? নাম ভুলে গেছি। কোশ্চেন কে করলা? শুভ্র, এই কোশ্চেনটা বুঝা গেছে কিনা? or everyone else?
জি স্যার, মানে 4টা বক্স থেকে স্যার -19 করে তারপর ডিভাইডেড বাই 3।
এক্স্যাক্টলি। সো ওইটা করলে আমাদের আলটিমেটলি এখানে 4টা ভ্যালু আসবে। এরপর ওরা যে জিনিসটা বলছে,
স্যার ইজ ইট অলওয়েজ ডিভাইডেড বাই 3 স্যার?
Yeah, it is always divided by 3.
আচ্ছা,
it is always divided by 3. That 3 is a fixed number because it's about the 3-dimensional relation. And once you get this thing, it says that use your answer in B to determine the pixel readings along the direction D3, the direction along the D4. And কথা হচ্ছে D3 directionটা খেয়াল করো। D3 হচ্ছে vertically down. So once you get these 4 numbers over here, the vertically down direction will be 2 numbers. So you should write 2 numbers over here with a bit of space. Or you can, if you want, you can make a rectangular box of 2 boxes and you can write those 2 numbers over here. However, there should be only 2 numbers over here. And D4 means in this direction. So if you are getting in this direction, you're gonna get A and then B plus D and then C. So you're gonna get 3 numbers over here. So in this case, you should write 3 numbers starting from the left. So what is interesting for you to see, have a look over here. What they're saying that either 5-4 or 14-5. So A plus D and B plus C or vice versa. So if someone do 14 plus 5, 14-5, তাহলে marks দিবো। Actually 14 plus 5 হওয়ার কথা না, because these pieces are gonna work like 2593. So 2593 যদি হয় তাহলে actually কত ভ্যালু হওয়ার কথা কত? Let me steal this up. আরে এটা আমি কপি করব কিভাবে এখন? এখানে যে ইয়া আইসা বসে আছে, কি বলে এটা, মিটিং কন্ট্রোল প্রচার। All right, let's say these are the values. So we're gonna get, according to the mark scheme, we're gonna get these values 2593. So if I write these numbers, we're gonna get 2593. So D4 direction যেটা সেটা হচ্ছে D3 হচ্ছে এদিকে vertically down, so we're gonna get 5 and 14. That's good. And then for the D4, so if we go for this diagonal relation D4, that is this one, we're gonna get 2, 8, 9. So 2, 8, 9. So starting from the very left, we're getting 2, 8, 9. And now this scan value would essentially be obtained in a diagonal set of values like this. So 2 over here, 8 over here, 9 over here. But for this answer space, you do not have diagonal spacing, you have horizontal spacing. So you might as well write these numbers like this: is 3 numbers, and inside number is 8. The outside numbers are 2, 9 or 9, 2. All right. Yeah, sure. This makes sense. That there should be 3 numbers written in this answer. So in this answer space that we have, you should have 3 numbers with visible gap. The mid number is supposed to be 8, and the 2 neighboring numbers should be 2, 9 or 9, 2. Now, one thing that I really wanted kids to see, have a look. If someone messes up this calculation by any means, they are gonna get different values for this table. Try to understand what I'm trying to say. First of all, if you subtract and eventually attending by division by 3, you do not get integer values. You should know that somehow you are making a mistake, because you are supposed to always get, for the sake of simplicity, integer values after for this pixel value, voxel values. For your syllabus, you're not gonna get fraction values. They don't show up. In real case, they might, but I didn't study about this, so I can confirm this information. But if you get any of these values wrong, for B number option, you're gonna lose that mark, because each of these individual values have a 1, 1, 1, 1 mark, 4 marks over here. But here's the deal: the moment you mess up any of these values, you're definitely gonna mess up these numbers. So which means any mess up in any of these 4 numbers is not gonna give you any ECF for this question. This question doesn't have any ECF. Have a look. These are very specific mention of numbers. There are no ECF. It doesn't say that you're gonna get this thing. So does it say? Oh no, it does say ECF. Sorry, ভুল বলছি। এই নাম্বারগুলো ভুল হলেও এখানে তোমাদেরকে ECF দিবে, ভুল বলছি, because it does show in the bracket that A plus D or B plus C or vice versa, which means if someone actually messes up these values, but in their wrong values, if they have done also this thing, they should get this. Sorry, disregard that information. You're still gonna get ECF marks for this one. So anyway, my point, বুঝা গেছে কিনা? এটা তো একটা গেল, এটা সিম্পল ছিল। আরো কিছু কোশ্চেন দেখি।
স্যার সাইড থেকে ওই অ্যাড করার জিনিসটা নিয়ে একটু কনফিউশন হচ্ছে আসলে।
কোনটা বলো?
মানে যখন স্যার আমি উপর থেকে হচ্ছে অ্যাড করতেছি বা হচ্ছে মানে 45 ডিগ্রি লেফট বা রাইট থেকে আর কি অ্যাড করতেছি, ওই জায়গাটাতে প্রবলেম হচ্ছে।
বলো কি সমস্যা হচ্ছে?
মানে স্যার D4 থেকে যখন আপনি ইয়ে করলেন, মানে আপনি বুঝবেন কিভাবে যে কোন নাম্বারগুলো আপনার আসতে হবে?
কারণ কোশ্চেন আমাকে দেখাই দিছে কোন ডিরেকশনটা D4।
স্যার তার মানে এই ডিরেকশনে আমার বেসিক্যালি হচ্ছে 19 এর একটা ভ্যালুতে অ্যাড করতে হবে, মানে টোটাল 19 হয় আর কি, 3 অ্যাড করে। লাইক B প্লাস D যে নাম্বারটা আসলো স্যার, ওই নাম্বারটা প্লাস A প্লাস C,
সেটা যে কোনো ডিরেকশন জন্য অ্যাপ্লিকেবল। For any of the direction, if you add up all the numbers, you're gonna get, that result should be 19.
আচ্ছা স্যার, কিন্তু B প্লাস D মানে আমরা আসলে ঠিক কোন অ্যারেঞ্জমেন্টে নিচ্ছি এটা কি ম্যাটার করবে না নাম্বারগুলো?
এটাই তো ম্যাটার করতেছে। D2 and D4 are different. Why? D2 would give you D, A plus C, B, whereas D4 is gonna give you A, B plus D, C. They're gonna have to be different because of the orientation. বলো কোন পার্টটা বুঝো নাই?
স্যার এই জিনিসটা মানে আরেকবার একটু অ্যান্সারটা দেখান তো, মানে আপনি কিভাবে অ্যান্সার করছিলেন D4 এর জন্য?
এই যে এইভাবে I got these numbers. G4 was this direction. So 2 comes as 2. 5 plus 3 gives you 8. 9 becomes 9.
ও আচ্ছা।
All right. Let's see a bit some other questions which might be helpful for us to have a bit more grasp.
স্যার ওরা মানে এমএস এ কেন স্যার তাহলে বলছো যে 2 or 9 হলে হবে, 9 or 2 হলেও হবে?
They were, I believe they are being, what can I say, lenient.
Yeah, maybe.
That's what I believe. আচ্ছা এই জিনিসটা দেখো, এখানে একটা জিনিস বলছে হচ্ছে এই যে সেই ডেসক্রিপটিভ কোশ্চেন যেগুলো তোমাকে বলছিলাম যে রিমোট সেন্সিং এর পার্ট থেকে গাদাখানি ডেসক্রিপটিভ কোশ্চেন হয়। ব্রিফলি এক্সপ্লেইন দ্য প্রিন্সিপলস অফ সিটি স্ক্যানিং। 6 marks. Scoring these 6 mark altogether can prove to be very difficult for a lot of candidates. I mean, regular candidates who have regular preparation might as well score 3 or 4. Good candidates might score 5, but to score 6 out of this question, you really have to know what you are dealing with. I'm going to discuss this question in detail because I just discussed how does a CT scan works, and there are multiple stages of operation and multiple ways of calculating this whole thing. So what are we going to write for 6 individually different information, which is going to credit you for a 6 mark. So let's have a look at the mark scheme for this answer, which is question number 14. Have a look at this one, so you can understand what we are handling over here. Here is 14. Have a look. We have 1, 2, 3, 4, 5, 6, 7 information. You can write any 6 of them. You can still score 6. So they have one additional information to go by. X-ray taken of a slice or plane or section. Anyhow, this information included gives you 1 mark. The scan is repeated at different angles. You can mention 4, or you can choose not to mention 4, but there will be multiple scans at different angles, scores you the 2nd mark. Images or data is processed by a computer typically, so they have to be processed. Process means you have to know the individual pixel value, and then they have to be done, something has to be done with them. So this information scores you another mark. Combined or added to give a 2D image of a slice. 2D image of a slice means what? 2D image of a slice means that whenever we are essentially doing this scan, for example, let's say this is a scan. Consider that this is a scan. This is a 3-dimensional object, but when we're scanning over here, these numbers are getting added together to get us this flat view of this linear section 5, 9. Whenever we're doing this one, these 2 numbers are getting added to give us a diagonal view of 1, 11, and 2. So here the individual voxel intensities are getting added up together to give us a linear view for this thing. So this is actually a voxel, where individual voxel have different voxel intensity. But whenever we'll do a scan, the result of the scan is basically coming out to be some fixed numbers, which is output of the addition of the voxel intensities. So that's the 3rd information that we have over here, which says that combined or added to give a 2D image of a slice, repeated for successive slice. Now this is the important bit. What does this mean? What does this mean by repeated by successive slide? এই জিনিসটা স্টুডেন্টদেরকে আমি বুঝাতে ইউজুয়ালি খুব একটু ঝামেলা হয়, বাট I'll try because you need to understand. Have a look. এই যে এখানে আমরা যতটুকু ইনফরমেশন দেখলাম হয়ে গেল, এখানে আমরা যতটুকু ইনফরমেশন দেখলাম যে this process of scanning, you have to understand these are 4 voxels which are being scanned from this side to begin with, and ultimately we get these numbers 4, 1, 2, 7. So this is along one line of the patient. So what do I want you to understand? So let me take this image and try to draw a patient around that image. That's what I want to do. Let's say এই হচ্ছে অবস্থা, let's say a patient, let me draw with brown people. Let's say this is a patient's body. Through this mechanism, we are actually measuring one slice of the patient. আচ্ছা, এটা actually 3 dimensional আমার এখানে বোঝানো difficult. আমি এর 2 dimensional একটা ভিউ আঁকি। মনে করো হচ্ছে এটা হচ্ছে আমার torso. This apparent rectangular box is my torso from the face. So this is my shoulders. This is the corner parts of my torso, and here are my legs, and then here is the head with a bit of a neck and hands coming out. A bit more realistic figure for a human being. For my standard, it's a very beautiful figure. So let's say this is a human being. If we want to scan this section of this person, let's say rectangle thickness. So let's say if we want to scan this much part of the human being, this process that we have seen over here essentially gives you the voxel values along one line, which means if I do this thing in this phase, if I do this scan for this phase for this patient's body, let's say we're gonna be able to get one line of voxel values, all the voxel values along this line. So that's one slice for the human body for this much space that we're handling. What do you mean by one line? So let's say here is 4217. So maybe along the depth of this line, you're gonna have 4. Behind 4, you're gonna have 1, and on the face you're gonna have 2, and behind 2 we're gonna have 7. So these are the 4 different voxel values that you're obtaining by doing one scan. This same thing have to be repeated for the next slice, for the next slice, for the next slice, for the next slice, and for the next slice. So you have to repeat this whole thing for multiple slices along the body. The X-ray machine does all of this scan simultaneously and eventually does the whole calculation. So the value of individual slice is calculated by a process which is shared over here. This process that we have shown for the multiple addition and eventually subtraction, background intensity subtraction, and dividing by 3, this has to be done for all the individual slices side by side to get the voxel value of all of those voxels. Because getting only one voxel, getting the voxel values for one line along the patient is not a complete diagnosis information. You have to have the 3-dimensional location for the entire tissue part that you're trying to scan the patient for. So that's important, that we are gonna have to scan slices of the patient body. So if I go in the sequence of the masking, have a look once again. Kids, you have to really understand what is happening over here, otherwise you cannot remember this thing. You can choose to memorize them, and in many cases that works, but I highly recommend that you understand what is happening. First of all, X-ray is taken in slice or plane section, repeated at different angles for the same section. Images or data is processed, which means it is somehow processed, combined or added to give a 2D image of the slice. This same thing is repeated for successive slices. To build up a 3D image can be viewed from different angles or image can be rotated. This last part of the information which I didn't tell you is that once we have the whole CT scan information, this information can be viewed in a software viewing capability in a 3-dimensional spatial arrangement. For example, let's say you did the CT scan for a patient's body and you have all the data, you can make up a tissue arrangement in terms of intensity variation. They'll say you did a CT scanning for a patient's inside, and then you can stack up all these numbers in a 3-dimensional viewing model where you can see different parts of this whole tissue arrangement by rotating this thing in a computer environment. So a 3D object cannot be viewed unless it is 3D printed, but 3D printing a patient's inside is not essentially very needed for the diagnosis because doctors only need to know what is there. They don't have to physically touch it to go for the treatment. So this entire information that we are collecting can be viewed in a computer environment from which you can take actual information. The way CT scan reports are usually made, which are printed on paper, is basically the section view, the slice section view of multiple layers where the anomaly is detected. For example, let's say in my let's say in the patient's body, if this part is the part of the body that is being undergoing CT scan, and let's say this segment of the body looks like this. So this is the face view, and inside the body we have, let's say, this much of a cuboid shift section that we are trying to scan. So it is not very properly drawn, but try to understand. So let's say this is the section of the body that we are trying to scan. Isometric view, but very weird isometric view. Actually এটা উল্টাকে ফেলছি, সামনের দিকে যদি এরকম হয় তাহলে পিছনের দিকে হবে আরো ছোট। সো মনে করো বডির ভিতরে 3 ডাইমেনশনাল যে কিউবটা আমরা স্ক্যান করতেছি, সে মনে করো সেই কিউবটার সাইজ মনে করো হচ্ছে এইটুকু মনে করো আমরা স্ক্যান করতেছি। নাও we just want to know what is in this place, or what is in this place, or what is in this place, where the anomaly is. And in the report of a CT scanning, what the doctors provide in terms of printed is that they print out sections of views of this anomaly, or section views of this anomaly, for doctors to be able to understand what is there. So the reports that we get from the CT scan diagnosis centers essentially tell us that in the part that we're did CT scanning, where did you have locations to be interested. They don't provide us the whole data, but the whole data can be obtained. If you ask for a CT scanning operator, they can give you a whole CD where the entire data is burned. They might charge you a bit extra for that, but you can have the whole CT scan data with you for that CT scan. For example, recently আমি আমার আব্বাকে BCH CT scan করাইছিলাম for a certain diagnosis process, and the doctor told us, our nephrologist told us that we should ask for the CD. They don't usually cover the CD in the regular package because it's an extra 200 taka, but you should ask for the CD. So I asked for the CD, and they said, okay, fine, we'll make the CD available for you, and we had it available for us. And you can, they give the software by which you should be able to see it within the CD, and also the data package for that patient within the CD as well. So you can install the software and eventually see it in 3-dimensional viewing for whenever you need it. So it's basically a way to build up a 3-dimensional image of a thing that you're scanning by having multiple iterations of 2-dimensional scannings. বুঝাতে পারছি কি?
Sorry, slicing এর এই পার্টটা আমি একটু কনফিউজ।
কোথায়?
মানে স্লাইস বলতে এখানে অ্যাকচুয়ালি কি মিন করছে?
স্লাইস বলতে এখানে মিন করতেছে হচ্ছে এই যে হয়ে গেল। স্লাইস বলতে এখানে মিন করতেছে হচ্ছে each of the vertical lines. For example, in this case you can see that if we do these 3 scans for this figure, so basically what we are doing, we have this 4, 1, 2, 7, this slice here. You can see there is actually one line of tissue. Do you see that? Or if I stack up more, 3 by 3 or 4 by 4, this is still one slice of tissue, one thickness of one voxel thickness. ঠিক না?
জি স্যার।
So by doing one set of scan, you're going to be able to detect the individual voxel value for one slice. That's one slice. But if you want to build up the whole 3-dimensional image for this whole thing, you have to go for this next slice, and then next slice, and the next one, and behind that, and behind that. All of these individual slices have to calculate, and eventually you can assign those voxel values individually.
Sorry, এখানে আমরা যেটা করলাম, this is just one particular slice. এরকম অনেকগুলো slice থাকবে।
Exactly, precisely. So that's why.
But sorry, these slices are not necessarily 2D. এগুলো তো 3D slices.
Well, each of these slices are essentially what we are considering to be a 2D image. The value of these slices, the thickness of this slice is basically equal to the voxel dimension that we are limited to, and the slice that you are having over here, which in this case is a 2 by 2 voxel size, these have some value. So this is what we're calling a 2D image. If you stack another set of slices over here, so in this case we're going to have 2 by 2 by 2, that will be a 3-dimensional block. This is still considered to be a piece of paper, or a 2-dimensional where you have thickness of one slice thickness. Then if you stack up multiple of this in front of it, for example, if I just take this image, and I would like to show you what do I mean by stacking it up. Let's say I do transfer selection and then copy it, and let's say this is stacking up. This would be the next slice, which wouldn't have the same values, but we have to scan that as well, and then this will be the next slice, and this will be there will be slices behind that as well. So we will have multiple individual slices stacking up together gives you the whole 3-dimensional data.
স্যার এতগুলো স্লাইস কোথা থেকে আসছে? রাইট, লাইক স্যার ডিফারেন্ট ডিরেকশন থেকে নিচ্ছি একটা স্লাইসের জন্যই তো।
এক্স্যাক্টলি, মনে করো হচ্ছে লেটস সে আমি বলি, মনে করো হচ্ছে এখানে ধরো আমরা মনে করো এখানে আমি যে হিউম্যান বডির যে পার্টটুকু আমরা স্ক্যান করতে যাচ্ছি, লেটস সে হিয়ার দ্য টোটাল horizontal length of this CT scan that you're trying to achieve, let's say এটা হচ্ছে মনে করো 10 সেন্টিমিটার। আমরা যে স্ক্যানার দিয়ে ভক্সেল যে সিটি স্ক্যানার দিয়ে কাজ করতেছি মনে করো সেটার ভক্সেল ডাইমেনশন হচ্ছে, let's say the voxel dimension is 0.1 centimeter. So it can detect the value of a 0.1 centimeter physical space. So 0.1 by 0.1 by 0.1, which means what? তোমার এই লাইন বরাবর তোমার মোট কতগুলা ভক্সেল থাকা পসিবল? 100টা ভক্সেল থাকা পসিবল না? 10 by 0.1 বুঝতেছো?
Yes, sir.
So which means what? You're gonna have 100 slices of this thing along this line, and you have to be able to calculate the individual voxel values for all of those 100 slices in individual different positions, which enables you to assign actual three-dimensional data.
স্যার মানে ফিক্স নাম্বার নাই আসলে স্লাইসের, তাই তো?
না নাই, এই আমাদের অ্যাকচুয়ালি কতগুলো স্লাইস আমাদের স্ক্যান করতে হবে depends upon two factors: how much big of a region do you want to scan, and how small is your voxel. Because the smaller your voxel, the more precise is the information, pretty much like an HD video. The smaller the voxel size, the pixel size, the picture looks crisp and more detailed. Similarly, if the voxel size is small, your diagnosis data would be more what can I say, more precise and more pinpointed, but it will require a much bigger amount of calculation power or data handling power for the computer or the software that you are gonna use. There is no fixed number for how many slices should you have to do for a certain voxel scan. Now, usually the doctors go for, I believe that this I'm not sure, but I believe that this thing is a variable. You can set this voxel value in your machine whenever you're going for a scan, because different part of the body might require different type of scan. For example, let's say if you're trying to find out the stage 1 cancer cells with CT scan, I'm not sure if they are achievable by CT scan, but let's say if you want to find a stage 1 means that it's not very spread out. It's in a single location, and the tumor is currently benign. It's not malignant. So for those cases, it's not very large. You might as well require very small voxel size, because you want to properly scan all the itsy-bitsy parts to find out very small indication of anomaly. But let's say whenever you are trying to find out a large grown-up tumor, you might not require that much of a small voxel size, because you know that tumor physically exists there. You might be feeling it from the outside. You just want to know exactly how big it is, or how deep it is within the tissue that where it grew up. Then you can then maybe the doctors can increase the voxel size. So depending upon what we want to scan, we can have it changed, but the changes that we're going to bring upon is going to definitely affect the process amount of data that we have to handle. বুঝছো কি?
জি স্যার।
রাফিদ বুঝা গেছে?
So that means যে 100টা voxel মানে সরি এই 100টা স্ক্যানটাকে then they integrate together to form the final 3D image.
Precisely, pretty much like a Rubik's cube. If that's easier to visualize.
And sir এখানে যেমন thicknessটা ছিল হচ্ছে কত যে 1 মানে there was 1 unit thickness, তো সব সময় কি আমাদের এরকম 1 unit thickness ই থাকবে প্রত্যেকটা?
Here's the deal: the physical dimension of the thickness can be varied. That's what I'm assuming, because it should be able to vary. I don't know this for a fact, but I guess the physical dimension of the pixel can be varied. But the way the process is executed is that we scan one layer or one slice, then we scan next slice. Practically, we don't do those scans one at a time. We get the total value in a single scan, and then we add them up in the computer environment for one slice at a time. মানে হচ্ছে, let's say we're gonna send the whole X-ray beam through this patient body over here. The detectors over in the back will be recording the individual pixel values along each of the slices, and then they're gonna remember that these slice values are these, and then they're gonna populate that table, and then they're gonna take the diagonal scan, let's say in a 40-degree angle, and add up with this thing. So each of the slices will be calculated individually, and then finally the individual absorption value voxel intensity of all of these voxels would be stacked up to give us the total three-dimensional value of the whole thing.
Sir, understood.
In a different way, if আচ্ছা না different way টা বলতে গেলে এখন বোঝা যাবে, বাট বুঝা গেছে কিনা, বুঝছো এটা?
Yes, sir, এখন বুঝছি।
Beautiful. Any further question, kids? People are leaving from the class, but okay, whoever you are still with me. Any other question? No. So we'll move on to the next part, which is the which is this one. No, is this one. The process how we can achieve. Can you should be able to explain the principles of, আচ্ছা আমি এই জিনিসটা যে জিনিসটা দেখতেছিলাম সেটা শেষ করে তারপর মুভ করি, এটা আসলে শেষ করা হয় নাই। Then images can be viewed from different angles or rotated. So we have a total of 7 different points over here. We can score 6. Have a look at the examiner's report. Many explanations were confused and inaccurate, including that most candidates did not appreciate how the image in CT scan was built up. Many thought that taking extreme images from many angles built up a three-dimensional image of the whole object, rather than an image of one film section through the object. This is the important bit. তিনটা ডিরেকশন থেকে একটা স্লাইসকে ভিউ করে থ্রি ডাইমেনশনাল ইমেজ হয় না, তিনটা ডিরেকশন থেকে একটা ইমেজকে ভিউ করে ওই স্লাইসের ইন্ডিভিজুয়াল ভ্যালুগুলো তুমি পাবা। In order to build up an image for the whole object, the procedure is repeated for further sections. This is the important bit that most of the kids did not understand or was not able to articulate properly. The two-dimensional images of the different sections are then used to build up the final three-dimensional image. Does the examination report make sense now? Hold on.
Yes, sir.
Acha. Here we have the same thing. And then if we go for some other questions of the voxel calculations are pretty much the same type of questions. I mean, actually we don't have much too difference in them. Okay. There are no more voxel calculations in my worksheet, but these are only up to W. These worksheets are up to, I think, 15 monohai. You can find out more questions later on. So if you look up for the recent years and go backwards. আচ্ছা, আমার piezoelectric crystalটা একটু বুঝাই। এই জিনিসটার basic operation, the core operation of this piezoelectric transducer was discussed in the first class of this thing. So we did talk about that, how this thing actually compressions and the refractions actually give rise to voltages. This is a property of the piezoelectric crystal, which is in this case is a silica crystal. So that's how they behave. Why they behave like this was not discussed. We are told that they behave. They behave in this manner. That's what we discussed. We can use this behavior to do two things at the same time. We can physically feed the crystal a certain frequency of voltage, high frequency voltage, to make them vibrate, which is going to work as a source of ultrasound. Ultrasound essentially means that physical vibration frequency will be more than 20 kilohertz, the upper threshold of our audible limit. So this silicate crystal can be used for two things. We can use these same silicate crystals to achieve two different things. We can primarily use it as a source of ultrasound. So if we provide the voltage from the outside circuit across these two silver plating, this voltage is going to cause the silicate crystal to vibrate. In that case, it will work as a transmitter of ultrasound. And this will keep on happening for as long as the duration of the duration of the pulse. Then if we stop the physical voltage sending and then now wait for the reflection to come back, then ultrasound pulses, let's say ultrasound pulses will be reflected off multiple different locations. What are those locations? I'm going to talk about them that in a bit. Ultrasound pulses is going to be reflected off multiple locations, and as they will be coming back to this silica crystal, that reflection is gonna set up another vibrations, compressions and refractions within the silica crystal. Now that rebound reflection is gonna be producing voltage across the silicate crystal. This is where the direction is happening. So we're using the same silicate crystal to first produce the ultrasound pulse, and then it will be reflected off multiple different boundaries, and the reflections are going to come back, and then those reflections are going to induce the voltage, alternating voltage on the silicate crystal, and we're going to be detecting that, and that's why the piezoelectric crystal or silicate crystal is going to work as a detection. So basically we're using this for a transmission and also for detection as well. So this type of things, what we call a transducer, not transducer, transceiver. So it can work as a transmitter. It can also work as a receiver. Together, the word is transceiver. Sometimes we also use the term probe. That's also a very common word. So this is how a typical ultrasound probe looks like in its long section. This is a very simplified view, and a highly simplified view. Let me show you how this physical object looks like. This is how an ultrasound probe looks like. This is a more general view of an ultrasound probe, or maybe this one. So here comes a wire. This is a face which is supposed to be attached to the to be touching the human skin. So we have all different shapes for different parts of the body that we're trying to scan. So we can have a lot of different shapes, but the idea is very simple. In this case, inside these things, we're gonna have a silicate crystal, which will be first vibrated by a sent pulse from wire, which is going to produce ultrasound pulse, and then it's going to be going to the patient's body, reflected off from different tissue boundaries, and then it will be detected over here after some time. So we're going to be sending a big, quite a good number of pulses over every second, and each of those reflections will be measured, and that can lead up to diagnosis, which I'm about to discuss right now. So this is a very, very basic structure. We have a basic thing over here, arch metal case. And then we have a coaxial cable, which is basically copper wire wrapped around with insulator material, which is wrapped around by a metal mesh, usually silver, or we can also have copper mesh. Good conducting material, metal mesh. This allows physical noises or external what can I say, voltage sources to stop disturbing our data. So that's the purpose of the coaxial. Coaxial cable আমাদের কমিউনিকেশন চ্যাপ্টার আর ডিটেইলস আলাপ আসবে, সো আপাতত এটা নিয়ে আমি কথা বলতেছি কম. We have a way to send a voltage through this wire, and the body is earth. So the way this whole thing works is that one part of the silicate crystal is always connected to earth, which is at zero potential. The other part of the silicate crystal is connected to this wire, this incoming wire. So if you provide a high positive voltage, then we're going to have one type of polarity across the silicate crystal. We have high voltage in one side, low voltage on the other one, might give you compression, and the vice versa will give you an rarefaction. So by sending the AC pulse over here, pulse means a short-lived AC signal. So not a continuous AC, like up and down sine curve, not continuous. So you send one group of sine curves for a small duration of time, and then you don't send anymore. That's what we call a pulse. So we send an AC pulse over here, which causes this piezoelectric thing to vibrate, and then you have a bit of a plastic cover. The plastic cover is over there only for protection. The backing material is pretty important. We need the backing material so that whenever the object is vibrated, it actually produces the vibration out of the plastic cover. Try to think about it. Whenever we'll provide voltage across the piezoelectric crystal, it will undergo this compression and rarefaction behavior. If we don't have anything for this silicate crystal to rest upon, then it will be vibrating back and forth in space. So it will be vibrating on both directions and compressing on both directions, trying to produce ultrasound pulses on both directions. But we do not want, practically, we do not need the ultrasound pulse to come out on this side. We would appreciate the ultrasound pulse to go out over here. So that's why we need a backing material. This is basically a piece of solid metal. It doesn't have to be very large, but this provides as an inertial support so that the vibrations come out on the right side. So this basically works as a resting surface for the piezoelectric crystal, so that whenever this is undergoing compressions and refractions, practically only the front end does the vibration and eventually produces the ultrasound pulses, and it comes out on the right side. Here we have on these two on this one, here we have a view for how does the diagnosis work. This is a very important figure that you really need to understand. Have a look at this thing. We have incident wave of intensity I coming in and falling onto a boundary of medium 1 and medium 2. The amount of energy that is incident on this boundary is gonna have two fate. Portion of the energy will be reflected off the boundary. This is represented as reflected wave intensity IR. Portion of the wave will be transmitted, or in other words, you can say it will be refracted. Transmitted is also a good word. This is represented as transmitted wave intensity IT. By the law of conservation of energy, we can always obviously say that the total incident intensity equals to the total reflection plus transmitted. This will always be true. So if you are sending, let's say, 1000 joule per second per meter square of intensity incoming, and you have these two things happening, certain portions reflected, certain portions transmitted, the sum of these two things would always add up to the original value, because we cannot create energy, we cannot destroy energy, can be only having converted from one form to another form or from one place to another place. So because of that, this equation will always be true. This is a very important equation, although it sounds very logical, like duh, but it's important for our calculation. It is going to play a pretty big role later on. So have a good look at this equation. If you wonder, will this always happen? The answer is a basic yes. We can design systems where one of them might be zero. For example, if you have total internal reflection, this never happens. In that case, I equals to IR, total internal reflection, if you remember from your O-level discussion, total internal reflection. Then again, you can design a certain mediums where the reflected intensity might as well be very small. Typically, reflected intensity is usually never zero, no matter what kind of pair of objects or medium that you choose or what kind of beam that you send. We always have some reflection. The reflection is, as far as I know, the reflected intensity is never perfectly zero. We cannot make it zero, but we can make it very small if we wanted to make it very small. But for the case of this process of ultrasound scanning, it is the reflected intensity which you are really interested about. Because you have to understand this part, that না ঠিক আছে একটু কোন জায়গায় বলছি ঠিক আছে আচ্ছা what you have to understand সেটা আমি একটু পরে বলতেছি but before I get into this equation, the actual mathematical procedure over here is very much equation dependent, but I'm going to try to actually give you an idea that how this whole process actually works. So discussion will be a bit lengthy, but bear with me because I'm trying to do this for you. Have a look. How does echolocation works? It's a bit interesting word. Echolocation. Echolocation is basically how does a sonar device works. Echolocation means that you will be producing a sound, pulse sound, not continuous sound, pulse sound from a certain location like beep or maybe ting or any type of pulse sound, and you're going to send out this sound in a direction or in all directions. This sound will be reflected off obstacles which are away from you, and it will pass through the medium. Might be air, might be water, might be solid, but it will be passing to the medium that you're sending it by. So as it will pass to the medium, first of all, it will undergo some amount of attenuation. Attenuation means the loss of power, because try to physically think. Let's say if we have, think about it. Let's say, let me give you a bit of an idea. Let's say here is water. I need to relook at myself to make this picture not aim to the sky. Let's say here we have some water. Here we have a submarine. Very common example. So submarine aiming this way. So submarine. Propellers are over here. So submarine aiming this way. Periscope. So this is and here we have some hills, or this is the end of a certain sea. From the tip of the submarine, it's going to produce the ultrasonic pulse, and that same device is going to be used as a receiver. So it's going to send out this pulse in this manner, which is going to get off, and eventually it will be reflected. Now here, this is the part that I want you to understand. The sound waves will be reflected over here in a certain pathway. Sound will be reflected over here from a different pathway. Sound will be reflected over here in a different pathway. If there is a large fish, let's say we have let's say we have Aquaman over here with legs and trident. So, okay. Let's say Aquaman is over here. Some part of these beams will also bouncing off from Aquaman as well. This is bound to happen. You have physical objects which are reflecting a portion of the wave. Now, you do understand that these green set of reflections are definitely going to take a much longer time compared to these orange reflections. This is obvious because this person is close and this boundary is farther, which means whenever this detector will detect these sound waves, these reflected sound waves, green sound waves, are going to be pretty weak because they have to travel through the water, these green sound waves, they have to travel through the water for a really long distance. The farther they go, the more spread out they become, and they lose energy because portion of the energy is transferred to the water molecule's kinetic energy, which is dissipated as heat. And you will not be receiving the same amount of intensity of this green wave as you send it from in this location. So because they have to cover a longer distance, they will be much dimmer. These orange sound waves, which are getting reflected of Aquaman's body, this would be in fact a much more stronger. So if you send out from here, let's say a sound wave of intensity, let's say 100% in all directions, whenever this green wave comes back, let's say that detected intensity is, let's say, 20%. Whenever the orange wave comes back from Aquaman, let's say that intensity is, let's say, 50%. This tells you that this is a stronger reflection. And also the amount of time which will be required for this wave to be back to the source and the amount of time that this will be back to the source would be different as well. This one is going to take a much longer time compared to this one. This will tell you that the reflection that is going to take a longer time to reach you back, that is reflected off from a far object. The one that is taking smaller time to reach you after reflection, that object is definitely closer. So here I'm trying to highlight precisely two information. One, how much time did the reflection take to reach to me since the point of production of the sound. So we made the pulse sound, let's say at t equals to 0. We're going to receive multiple reflections from multiple objects around us. Some reflections are coming us earlier, some reflections are coming us later. So reflections which are reaching us at an earlier time are getting reflected off a boundary which is closer to us, and vice versa. So this time information is very important because it is that measurement of the time combined with the velocity of the sound within that medium can tell us precisely where that reflection happened, or how far is that reflection boundary. In this case, let's say Aquaman's body, where is that reflection is happening from. So we can precisely measure how far is the reflection surface if we have a precise way to measure the time for how much did this happen. This goes with a very simple equation that you have come across to study in your O levels. V equals to 2d by t. 2d because the d this is covered twice. So if you subtract d, you get vt by 2. So we should know from our earlier experience what is the value of V over here. Maybe in seawater, different at a specific temperature, you have certain speed of sound. In human body, you have certain different speed, which we know from experience, and we have measured it by other mechanisms. So it goes. So it's important that if we can somehow measure this value of T very precisely, if we can achieve to measure this thing, we'll be able to say how far this D is. That's an important information. One. Second important information is that how strong is the reflection is also going to be important for us. For example, if here is Aquaman and here is this thing, and let's say if here is Amber Heard right over here, I hate this woman. Now, let's say Amber Heard has been replaced with Emilia Clarke. So let's say here we have Emilia Clarke over here, and let's say, yeah, obviously. From 9 gig, I have very good replacement for Amber Heard. I hope it is Emilia Clarke, or we can also have what's the name of this girl? Abernethy, Dolores Abernethy from Westworld. Anyone know the actual name of this actress? Anyone? Wait. Interesting discussion. So I'm taking my time to show you. Dolores Abernethy, actress.
Sir, Evan Rachel Wood.
Yes, Evan Rachel Wood. So either of these two women can replace that character. They are both very strong as per their drawing, acting so far. So, yeah. So let's say, so let's say here is Aquaman, the blue guy, wearing a very strong armor. Here is Emilia Clarke, not wearing a very strong armor because she has Aquaman to protect her, whatever. So the intensity of reflection of these sound waves would be different from their skins. Aquaman's armor is going to reflect from a very strong surface. So these reflections are going to be pretty strong from Aquaman's armors. Maybe Emilia Clarke is not wearing that much of a strong armor because whatever reason. And the reflection from her skin or from her costume, from her dress, is going to be weaker because that reflection surface is soft compared to the armor of Aquaman. Which means depending upon how strong or how weak of a reflection you're going to receive over here, you can somehow have a measure that how strong / how hard that reflection surface is. So if some sound, let's say if some ultrasound inside a patient's body is reflected off a fat flesh boundary, the reason I'm just saying fat flesh boundary because for those who have biology, you have a bit of an idea about this. For those of you who, oh no, আমার এখানে মামুন আছে। I'll have to pick this out later. For the time being, let's go in airplane mode. Okay, কি বলছিলাম? কি বলছিলাম? Help me remember. কি বলছিলাম যেন?
আর্মার মানে একটা উইক হয়ে
আচ্ছা হ্যাঁ for those who have biology you have a bit of an idea for how the human body structure is. For those of you who don't have a biology, this is how it looks. Let's say this is skin. Let's say this is skin. Inside the skin we have fat. So let's say this line is skin. So this let me just draw a thin thickness. Let's say this is skin. Let's say after the skin we have a bit of a fat. So if you wonder, we don't have fat everywhere. Yes, we don't have fat everywhere, but we have fat in most places, more or less. So consider that this is fat. Beyond the fat, typically we have flesh, muscle. So let's say we have a layer of muscle. Beyond the muscle, we have the actual physical structure that we have. Now, a very easy example to deal with is the thigh, because thigh has a single bone, femur, and there is no open space like stomach or lungs where we have to deal with actual air cavities. So consider thigh for a simpler representation. So if you consider thigh, skin of the thigh, fat of the thigh, muscles of the thigh, the ghost and everything, then we have the bone. So let's say this is the, then we have this part, which is the bone. So we have the bone over here. And what happens after that? The whole thing that is over here will be replicated on the right side, which means right after this bone is finished, we're gonna have muscle. Right after the muscle is finished, we're gonna have fat. And right after the fat is finished, we're gonna have skin. And on the left of the skin, we have air. On the right of the skin, we have air. So this is a very basic representation for how a human body can be standardizedly considered. That we have skin, fat, muscle, bone, muscle, fat, skin. A very basic idea. Now, every single time, let's say we are about to make an ultrasound scan of this part of the body, let's say. So we're gonna place the probe over here. We need to have some gel over here to reduce the impedance, but ওই জেলের কথা একটু পরে বলছি। মনে করো এখানে আমরা আল্ট্রাসাউন্ড সোর্সটা এখানে দিলাম, সো এখান থেকে আমরা একটা হাই ফ্রিকোয়েন্সি সাউন্ড প্রডিউস করব। সো here's a part you need to understand. The ultrasound will enter. Let me use a blue for this thing, and let me zoom in over here, so it might be a bit more easily understandable. So this ultrasound is entering from here into the body. Is gonna first undergo a medium change from skin into fat. This is a medium change. So in this happening of medium change, we'll have a bit of this. We're gonna have a bit of this. We're gonna have this incident happening. Certain part will be transmitted through, certain part will be reflected. The reflected part will be coming back to the detector. The transmitted part will enter the fat tissue and it will travel. Here we're gonna have another of this thing. Now this ultrasound is gonna travel from what? From fat into what is this layer? Anyone?
So muscle.
This
Or
label as muscle. So now this ultrasound will be traveling from fat into muscle. This will give us another of this happening, a bit of reflection, a bit of transmission. Then the amount that is reflected will be eventually coming back to the source and it can be detected. Then the sound will, the remaining transmitted part will be traveling through, and now it will be hitting the bone. I'm not going to go further down. I could, but for the timing I'm deciding not to, because I'll go for the example for brain as well. This is the hardest of the surface, so this sound will be, let's say, mostly reflected off from the bone surface, and it will once again travel through here. But interesting thing happens. Here's the part that I really wanted to understand. Once the sound will once again come back and start reflecting, let's say, as it was going, we had transmission, reflection, transmission, reflection. And let's say over here we have a bit of transmission and reflection. When this sound wave will be coming back and it will enter from muscle into fat, it will once again have the same happening. It will also, a certain portion will be transmitted and a certain portion will be reflected into this section, which we cannot detect. So the moment any wave will undergo medium change, it will undergo this happening. What happening? This happening. Certain part would be reflected, certain part will be transmitted. And then how much part is transmitted and how much part is reflected, we have a set of equation to analyze that. And ultimately we can detect how much part of that intensity did we receive over here. An important bit all of these individual reflections that we're gonna get are gonna be detected at different time frame, because the further the reflection is happening from the source, more time will be required for that sound wave to come back to the source. Depending on this time variation and depending upon the intensity, we can decide that exactly what is the construction of the body tissues along that line of the sound traveling. So how thick is the fat layer, or what kind of fat is there? Is it soft fat or is it hard fat? And how big is the muscle layer? Is it solid muscle, or is this muscle filled up with fat, with fascia and other stuffs? So we can have precise information that what medium is present at certain locations and what are the dimensions of those locations, or what is the locations of this exact reflection surfaces where the medium changes are occurring every single time the medium change occurs. Each of this information will be fed back to the over here, and the way this thing produces ultrasound, let's say the one way I can show you, this figure is not done to scale. Let's say this is the intensity versus time. I should not draw intensity. Let's say this is the amplitude versus time of the fed ultrasound. Let's say we're gonna send one pulse of very high frequency pulse, and then we're not gonna send anything. So then what's gonna happen? We're gonna detect multiple reflections along the path, and the computer has a way to know that what is the maximum amount of time that it could require for the sound to travel all the way to the bone and eventually come back. It knows this thing. Let's say for a certain scenario, let's say if that duration is, let's say, 2 seconds, which is not supposed to be 2 seconds ever, but let's say it's 2 seconds, which means the next ultrasound pass. So within the 2 seconds, all the sound will be back to the source. So you can send the next wave pulse after 2 seconds. So let's say this much gap over here should be at least 2 seconds, so you don't have overlapping data. So you send one pulse, receive all of its possible reflections, you allow the time for all the possible reflections to come back to you, and then you send the next pulse, and then you have the whole thing again. Then you send the next pulse, then you have the whole thing again. Because we are working with ultrasound, the sound can travel pretty fast, and also depending upon how much of a thickness of a human body are we measuring, this time gap can be controlled. For example, if you're really trying to take a ultrasound scan of a thigh, regular person thigh, not typical American, regular person. So if you're taking a thigh for a regular person, then we're gonna have a certain thickness measurement. So that would give us a certain value. But if you're trying to take a prenatal scanning or the ultrasound scan for an unborn baby, then we need to scan from the surface of the belly of the mom all the way to the backbone and eventually all the way up. So the amount of distance that you need to cover over here is bigger. So to accommodate for that much distance, we need to send these pulses less often. Less often means with a bigger time gap. So depending upon what exact part of the body we are scanning, we can calibrate for how often are we going to send those send pulses. But after we send one pulse, there will be multiple reflections detected depending upon each of the boundary changes that sound wave have to go through. And how much intensity did you detect and how late did we detect will tell us two information: how hard or soft that surface is, and where is that located, or what is the thickness of that boundary is. Together, these two information give us one line of data. Now, this is a very important information. Have a look. Ultrasound scanning, one single pathway for this ultrasound wave basically is a linear scan. It tells you exactly in one dimension along the length of the path of the ultrasound what is in that path. To be able to produce a two-dimensional image, we have to stack up multiple of these scans, hundreds or thousands or maybe millions of these scans for all the region. That's why whenever the ultrasound scan is done, if any of you have seen how an ultrasound scan is done for an unborn baby, that probe is aimed towards the backbone and it is rubbed along the entire ovum to na ki bole pet, the whole underbelly, so where the baby is there. So this ultrasound scanner is moved along the entire skin so that we can get a lot of linear data. And then when we stack up all of this data in a computer environment, we get a two-dimensional image of this thing. And places where the baby is located, we have more absorption. Those locations are colored with a bit light pixel, for example, whitish pixel. Places where it takes less time, where we receive a bit more stronger reflection. Maybe the baby was not there in those locations, so we get a much higher reflected ray. So we practically measure the value of intensity of the reflected ultrasound wave, which was reflected at the backbone at the end as the end border. And between the ultrasound probe and the backbone, somehow we have the flesh, tissue, amniotic fluid, we have the baby, and we have the uterus walls, the before and after, and we have the whole thing. And in that process, it actually scans up the whole thing, and we get the ultrasound scanner or the probe basically can measure that what intensity of sound wave did it measure. It does not sense any color. Later, individual intensity of these sound waves are given different color for us to be able to have a contrasted picture for which our eye is comfortable. So the typical picture that we come to see from an ultrasound scan, that we have baby shape, bright and dark, the sensor does not detect bright and dark. The sensor detects intensity. So it gives one type of color to more intensity, it gives a different color or shaded color to light intensities, and that light and dark image gives us a contrasted image of the unborn baby, or whatever that is that we're trying to scan. For example, if you're trying to scan, not trying to scan an unborn baby, let's say we are trying to scan a thigh of a certain person where there might be a tumor inside the patient's feet, then it's possible that let's say a regular person's foot scan or thigh scan should look like this. But a person who have developed a tumor might as well have an unnatural large reflections over here, which is the anomaly. That anomaly can tell us exactly where the tumor is, how big the tumor is, and all this other information. So comparison with regular, the difference with the regular is what is we are trying to diagnose. এই পর্যন্ত বুঝা গেছে কিনা?
স্যার টাইম ডিউরেশনটা ম্যাটার করতেছে না এখানে? তাহলে
টাইম ডিউরেশন ম্যাটার করতেছে তো,
মানে ইন্টেন্সিটির ওখানে ক্যালকুলেশনে টাইম ডিউরেশন আসতেছে।
হ্যাঁ, দুটো ইনফরমেশন সাইমালটেনিয়াসলি হ্যান্ডেল করা হয়। একটা হচ্ছে how much intensity did we receive for reflection and how late was this reflection received from the sending point. So the value of the intensity tells us how hard or soft the reflection is. That duration tells us how far is that located. We have to use both of these information together to produce that image.
স্যার হোয়াট অ্যাবাউট মানে যে কন্ট্রাস্ট হবে যে ইমেজের ভেতরে, ওইটা কিভাবে বুঝতেছে?
ওটা বুঝতেছে না, ওটা ডিফারেন্ট ইন্টেন্সিটিকে সে ডিফারেন্ট কালার দিয়ে রিপ্রেজেন্ট করতেছে।
ও আচ্ছা,
ওকে, হ্যাঁ, আবিয়াস বলো। আচ্ছা, you are about to write, sorry. What if we get reflected sound from the chair and the bed, and are they made specially absorbed to the sound? Okay, I'll tell you. You're saying about the chair and the bed that the patient is located on, right? Acha. There is a very important thing. We can actually discuss this and conclude today's class. সেটা হচ্ছে how much amount of a sound is going to be reflected off from the surfaces from a boundary change is largely dependent upon a physical factor which is given in this paragraph, which is called the acoustic impedance of a medium. It's a term, it's called specific acoustic impedance. Z is the term for a certain physical medium, and it is given by rho into C. I don't know why they decided to use C, because C is the typical symbol for light wave, but they did, you can remember as V as well. Rho is the physical density of the medium, physical density, kg per meter cube, and C in this case is the speed of the wave through that medium. So if you product these two things, you get a certain quantity, which is called the specific acoustic impedance of that medium. This is the equation that relates the reflected intensity with the incoming intensity. So IR by I is given by Z2 minus Z1 whole square, or Z2 minus Z2 plus Z1 whole square. Big or small doesn't matter because we are squaring this thing. but you have to understand that the subtraction goes on the numerator side, the addition goes on the denominator side, because obviously this fraction cannot be bigger than 1. So unless you are really dumb at maths, you cannot mess this up. IR by I equals to subtraction square divided by addition square. So এটা হচ্ছে ইকুয়েশন। এই ইকুয়েশনটা কোত্থেকে আসছে, ডিডাকশন কিরকম, এটা কোত্থেকে কে বাই করলো, এগুলো আমাদের লাগবে না। ইউ জাস্ট হ্যাভ টু নো দিস ইকুয়েশন বাই ইয়োর হার্ট এন্ড বি এবল টু ইউজ ইট ইন অ্যাপ্রোপ্রিয়েট প্লেসেস। এই ইকুয়েশনটা আমাদের ফর্মুলা শিটে দেওয়া থাকবে না। ইউ হ্যাভ টু নো দিস। The weight, what really happens if you have a look over here, that air has a Z of about 430, but the other stuffs, quartz, water, blood, fat, muscle, they have a really different value of acoustic impedance, which means if whenever sound will be traveling from any medium to air or air into any medium, the amount of reflection would be extremely weak, because this difference would be very small. This is why we prefer to avoid air for an ultrasound scan. So what I'm trying to mean is this. No, Amber heard no. So what I want to mean is that if we are trying to scan over here, I mean, when the way the ultrasound scan works, we prefer to avoid air. So to avoid the air, typically the technician or the doctor, they place a certain gel on the human skin, which works as a coupling medium. That's the word. Coupling medium means that gel is specially designed in a way that it has the similar acoustic impedance of a human flesh. So using that gel in between this, let me show that gel with, let's say maybe purple. So placing that gel between the sensor probe and the skin takes out the air out of the equation. So that way we can send a very strong ultrasound pulse into the patient's body. As a result, it becomes easier for the detector to do its job. But if we did not use the gel, if we directly rub it on the patient's body without using the gel, then in that case, there will be a significant reflection of the ultrasound boundary into the air. And as this thing would enter from air into the patient's body, a very weak signal will be entering the patient's body. So that's why we use the coupling medium. Now, why am I bringing the idea of coupling medium for your answer? Because I want to understand that the moment the sound is coming out into air, it is largely absorbed. So the question that you asked, that is it impossible for us to have the reflection from those places? The answer is no. We can very well have reflection from those places. I mean, technically speaking, can we have it? Yes. Is it going to matter by any amount of significance? No. বুঝছো কি বলছে? হ্যালো,
স্যার যখন এয়ার থেকে ওই মিডিয়ামটাতে যাবে ইন দ্য জেল, তখন একটা সিগনিফিক্যান্ট রিফ্লেকশন হবে না, সিন্স দ্যাট জেল ইজ অলমোস্ট সিমিলার টু
হ্যাঁ হবে, but the thing is, I mean, we want significant portion of this thing to be reflected into the bits. That's the point I'm doing, that this gel is designed to have as a nearly equal specific acoustic impedance as the human skin. And যদি আমাদের Z1 আর Z2 nearly equal হয়, এই ইকুয়েশনে দেখো, if Z1 আর Z2 nearly equal, তাহলে আমাদের এই ফ্র্যাকশনটা 0 হয়ে যাচ্ছে না?
জি স্যার।
তার মানে আমাদের রিফ্লেক্টেড ইন্টেন্সিটি হবে অনেক উইক। তা which means what? Reflected intensity যদি উইক হয়, তার মানে ট্রান্সমিটেড ইন্টেন্সিটি হচ্ছে nearly equal to the same intensity. So we make that gel to have nearly the same acoustic impedance for typical human skin. As a result, because of using that gel, at the entry, the reflection would be very weak, which means most of the sent energy from the piezoelectric transducer, the silica crystal, would be entering the body. That's essentially what we are after. Or in other words, that gel would practically work like a thicker human skin.
couldn't we have done something to directly মানে এরকম একটা, ও আচ্ছা স্যার, এখানে কি আমরা এয়ারের সাথে কন্টাক্টটা মিনিমাইজ করার জন্য এটা করছি?
Exactly, precisely, that's the aim. We don't want air to be in between, because air has a very different Z value, which makes the whole measurement skyrocket towards diminishing results. বুঝা গেছে? Did you get your question answered?
Yes, sir.
আচ্ছা, Abias, did you get your question answered? I can see a yes written in the chat window, but I'm not sure when did you write this. You still have your hand raised. Acha, if you have further question, maybe we can pick it up next class. Have your sort handled. আচ্ছা, আপাতত আজকে এই পর্যন্ত থাক। আমি এই কোশ্চেন পর্যন্ত বললাম, আমি এই পরের এই কোশ্চেন থেকে ইনশাআল্লাহ নেক্সট ক্লাসে আলাপ করব। And then we have some stuffs over here with the HVT value, half value thickness, and some relevant calculation. One thing I really want you kids to understand that ultrasound scanning এর basic এই যে piezoelectric transducer working principle আছে, টোটাল রিমোট সেন্সিং এর ফুল চ্যাপ্টারের মধ্যে সিগনিফিক্যান্ট ম্যাথ হচ্ছে এই টপিক থেকে। সিগনিফিক্যান্ট ম্যাথ এর পরের টপিকটা হচ্ছে যেটা আমরা নেক্সট ক্লাসে দেখব, সেটা the last topic for the remote sensing of the medical imaging process is MRI, magnetic resonance imaging. There is zero mathematical calculation about this. This is all theoretical. You just have to say how it works. What is the underlying principle? What do you do? What do you try to detect? What do you try to change? Blah, blah, blah. No math from here. So you basically have math from two places. একটা হচ্ছে এটা যেটা এখন পড়াচ্ছি, ultrasound scanning, or there are some rectangular math calculation for this thing, which is also not so very common. So this topic of ultrasound scanning is basically the mathematical part of the medical imaging section. So might as well be very more interesting, or you can say more important for it. Okay, so if T is almost equal to R, then it doesn't really matter. Oh, hold up. IT almost equal to R means that you have 50% reflected, 50% transmitted. We want for the coupling medium thing, for the gel or the coupling medium thing, we actually are trying to make the IR as close as zero as possible. That's what I said, that the coupling medium or that gel that we use on the skin has nearly the same Z value as human skin. So it basically works like a thicker human skin, but it does not actually reflect much whenever the sound travels from that gel into the skin, because they both pretty much have the same acoustic impedance, which means R is nearly zero, which means most of the part is transmitted, which means a significant stronger signal enters into the body. So the question that you asked is that, the answer that I gave you for your earlier question is that we are going to have reflection of the chair and the bed or the neighboring particles, but we are going to have it. I mean, if the question is asked, are we going to have reflections of those things or not? The answer is yes, we are going to have reflections. But is it going to matter to our measurement? The answer is no. বুঝছো কি বলছে? Yes, precisely. এখন ঠিক আছে। বলবান, আজকে এইটুকু থাক। Thank you for the additional 31 minutes of attention. I really appreciate this for those who stuck by. You can pick up your worksheets tomorrow. আর হচ্ছে ফিদা, I'm handling your situation. Just make sure that you have received them by day after tomorrow. If you haven't, let me know about it. Good night. Allah Hafiz.